Alright guys, let's continue talking about our second part here, which is acids and bases. So the first kind of question we're going to talk about is how is pH related to the concentration of hydronium ions, which are identified as H plus or H3O plus, and hydroxide ions, which are OH minus. So there are three main definitions of acids and bases. The Arrhenius definition is kind of the first definition that was made of acids and bases, and it talked about them only in a water solution. And the way it was described is that acids produce a hydronium ion, or H+, and bases produce an OH- or hydroxide ion in solution. This is true for a lot of acids and bases, but there are a few types of molecules that do not follow these rules that are acidic and basic. So Bronsted-Lowry was a second kind of scientific pair that came up with their definition of acids and bases, which are in any type of solvent, because water isn't our only solvent. We can also dissolve things in benzene, and other solutions. And so in this definition, acids donate the H+, and bases accept that H+. So in this definition, acids are donating an H+, and bases are accepting that H+. Lewis acids and bases, which are used mostly in organic chemistry and have kind of the best definition for a wider range of substances, is that acids accept an electron and bases donate that electron. We're going to talk mostly in regards to Bronsted-Lowry's definition of acids and bases in this class, and Lewis acids and bases a little bit later in class. So this is a Bronsted-Lowry acid-base reaction. We have our acid here with an H plus some other stuff, so like HCl reacting with our base in this case. This H plus is being donated to the base, so we're left over with what's called a conjugate base and a conjugate acid. The conjugate base is formed from the acid when it loses its hydronium ion. The base becomes a conjugate acid when it gains the hydronium ion from the acid. And so we call this the conjugate acid-base pair, which is related to the original acid and base when the acid donates that H+ to the base. Ionization is the process of an ion becoming a solution, or an ion in solution, and this is what makes acids have their strength. So strong acids are strong because they ionize 100% in solution. They turn completely into that hydronium ion, which we represent as either H3O+ or H+. Weak acids and bases then, they're weak because they only partially ionize. They only partially give that hydronium ion in solution. So this first reaction is HCl, and HCl, when it dissolves in solution, is a strong acid because it 100% ionizes. 100% of the hydrogen that is attached to the chlorine separates into H+, meaning it's giving us more of that acid hydronium in that solution. H2S is a weak acid because it doesn't 100% ionize. Notice that the H, there is still an H attached to the sulfur in the right side of our reaction. The other thing we notice in this type of reaction is that the arrow is different. In a 100% ionization reaction, we have a one-way arrow pointing from reactants to products. In a weak acid or base, we only partially ionize, meaning that we're kind of going back and forth between our acid and our solution. And so we actually have a two-way arrow because ions are kind of going back and forth. And when we get to our last unit on equilibrium, we'll talk about how we can shift reactions to go one direction towards product or the other direction towards reactants based on changing some different variables regarding that reaction. So the key takeaway here is that strong acids are strong because they 100% ionize. They become 100% H+ in solution, where weak acids and bases only partially ionize in solution. And this applies to bases too, not just acids. So let's take a look. This is a list of 6 strong acids and bases. If you Google search this, you might find a list of 7, or they might vary very slightly, but this is the pretty generic go-to list of which bases and acids are strong. If you were taking an advanced chemistry class, you would just need to know that these are your strong acids and bases. I'm not going to ask you to memorize that, but these are the ones that are going to 100% ionize in solution and are our strong acids. So we have perchloric acid, hydrochloric acid, hydrobromic acid, hydroiodic acid, one of my favorites, nitric acid, and sulfuric acid. Our bases, lithium hydroxide, sodium hydroxide, potassium hydroxide, notice the theme, calcium hydroxide, strontium hydroxide, and barium hydroxide. So these are our acids and bases, again, that are going to 100% ionize in solution. Any other acid or base in solution is going to be weak, meaning it's only going to partially ionize and break into that hydronium ion. So how do we measure the strength of acids and bases? We use what's known as pH, and you've seen this before, I'm sure, a million times. But pH stands for the power of hydrogen. And when we talk about power in this case, we're talking about a logarithmic measure. So when we say 10 to the blank power, that's our logarithm there. So pH is the power of that hydronium ion in the solution. So it's our way of measuring how much of that hydronium ion we have. Water is defined as neutral, meaning it has a pH of 7. It is equal parts acid and equal parts base. So the pH of water is 7 and the pOH of water is 7. You may not have ever looked at pOH, and pOH stands for the power of hydroxide. And so this simple equation here, which we have pH plus pOH equal to 14, can allow us to convert between these two scales. We're very used to hearing about pH. We often don't refer to things as pOH, but really they're just the inverses of each other. So if something is to have a pH of 1, it actually has a pOH of 13. Acids are going to have low pHs. Bases are going to have high pHs. Bases are going to have low pOHs, and acids are going to have high pOHs. And it should make sense if you understand logarithms. If not, just understanding the fact that we relate to things in pOH and that acids have that lower number of the hydronium ion concentration. All right, so let's do a simple problem here. Like I said, if a solution has a pH of 3, what is its pOH? So if I have a pH of 3, I don't know my pOH. I know that the sum of those two is equal to 14. So I can solve for my pOH, which is 11. pH and pOH is a unitless measurement, meaning there is no unit after 11. You would just say the pH is 11. There's no like meters or seconds or anything that follows it. The second or kind of final part we're going to talk about is neutralization. And so oftentimes in life we need to neutralize a situation or a substance in order to make it safe. And so a chemical reaction where an acid or base are combined, destroying the properties of both is going to produce water and salt. So whenever you have an acid and base reaction, you're always going to be producing water and salt. And so this is the basic hydrochloric acid and sodium hydroxide producing NaCl and water. It is also a form of double replacement reaction, if you can kind of see that happening. So how do we know if we have an acidic or basic solution? We can use indicators. And so an acid-base indicator is usually a weak acid or base that exhibits a color change when hydrogen ions or hydroxide ions are present in solution. You've probably done this with like litmus paper, and you've put like a pink piece of paper or a blue piece of paper in a solution, and if it turns blue, then it's blank. If it turns red, it's blank. Those were a type of indicator. They're often used in titration, which is a scientific method of identifying acid-base reactions. We aren't going to go into those, but if you took a more advanced chemistry course, titration is very useful in identification of unknowns. So color indicators, the universal indicator is my favorite. It's the easiest to use. You can use it universally, meaning you can use it with any type of solution, acid or base, and it gives you this like rainbow effect for what type of pH you have. So if it's more red, you're going to have a low pH acid. If it's more purple, you're going to have a high pH base. Phenolphthalein is one that's used in that titration. It's going to turn pink in the presence of a base, and it stays clear in the presence of an acid. You can use methyl orange, thymol blue, bromethyl blue, and phenol red, depending on the type of solution you have and kind of what you're looking for as to indicate pH. There are also electronic pH indicators, which can electronically measure the presence of hydrogen or hydronium ion concentration, and those are obviously are much more precise than just a color change method. So we have some strong acids, weak acids, strong base, weak bases. In a chemical reaction, the way we represent these is different because remember the ionization. So in a strong acid, we have a one direction arrow because we are 100% ionizing this HCl into hydronium ion or H+ ion. So if I have a strong acid in water, I'm producing 100% H+ and 100% Cl- in that H2O solution. If I have a weak acid, however, I have a two-way arrow. I only have some of that weak acid. This is acetic acid, which is vinegar, reacting with water. That's going to produce a little bit of the acetate ion and a little bit of the H+. But it's not 100% going. That's why we don't use the one-way arrow. This is a two-way street here where we can go back and forth between reactants and products. Same thing with strong bases. We have our sodium hydroxide reacting with our H2O. Sodium and hydroxide are going to 100% ionize in solution, and that's because sodium hydroxide is a strong base. Weak bases like ammonia here is only going to partially ionize in solution, and that's why we use a two-way arrow. So if you see a two-way arrow, you can identify that as a weak acid or base. The one-way arrow is going to help you indicate that it is a strong acid or base. So in a neutralization reaction, this is kind of where our practice comes into play. Can you complete the type of reaction, or can you complete what products are going to form based on what you have here? And so you're going to need to use your strong acid, strong base chart, and also your knowledge on balancing equations that we did a couple units ago. So in this case, we have sulfuric acid reacting with magnesium hydroxide. We need to then produce, magnesium is going to form a bond with sulfuric acid, and water is going to be formed because when I neutralize a solution, so when we write these neutralization reactions, notice that water is always a product. And so we're forming a salt. So salt isn't always NaCl. Salt can be any form of cation and anion formed from this type of reaction. So that salt is going to be formed from what I call, or what most people call, spectator ions. So in an acid-base reaction, really what's happening is we have this hydronium ion and this hydroxide ion reacting to form that water. And these guys over here are really just hanging out. They are sitting on the bleachers. They're not really participating in the reaction. They usually have no effect on the reaction. So sulfuric acid, sulfate in this case, and magnesium are the two spectator ions that then go to form the salt in that neutralization reaction. So in this one, we have hydroiodic acid and potassium hydroxide reacting to form potassium iodide and water. So potassium iodide in this case would be our salt, formed from the spectator ions of potassium and iodine here in that solution. Balancing the reactions, remember, is always important. You can't finish a chemical reaction without balancing. It's incomplete. So keep in mind when you get those reactions that you will need to balance them to make sure that they are complete. All right, so can you, after both of these videos, identify and write neutralization reactions, calculate and use pH/pOH to classify a solution as an acid or a base, explain what makes an acid or base strong versus weak, compare and contrast Arrhenius, Bronsted-Lowry, and Lewis acid-base pairs, and then back to that first video on molarity and different types of solutions. So if you need to go back to any parts of these videos to make sure that you can do these types of questions, that would be helpful. In your 12.3 or 11. Oh, I didn't change these numbers. Sorry, guys. In your 12.3 assignment, you'll be practicing each of these types of questions, and then you will have your concept check and your summative quiz.